Okay, so I'd like to thank the organizers for the chance to talk here. So my talk is going to be, there's going to be some holography at the end of it. You see this probably, I'm not sure if there had been any talks that involved any aspects of cosmology. But the idea here is to talk about, to contrast weak and strong coupling approaches to understand non-equilibrium dynamics in the early universe. It's based on this paper here and this most recent paper here. Came up a few months ago. So the long-term goal of this research, at least the things that I'm interested in, is to understand how standard model fields can decohere towards a thermal state. So how do standard model fields, like, for example, the one is in the QCD Lagrangian, how do these fields can evolve towards a thermal state? Right? It's far from being understood, and actually gives you an interesting link to cosmology. For example, if you see this cartoon, the only interesting thing about this cartoon for me in this talk is going to be that here in this thermal history of the universe, you see that the QCD phase transition was around here, a few microseconds after the Big Bang. The temperature was 150 MeV, while the electroweak phase transition happened earlier in 20 picoseconds, and the temperature was 100 GeV. So within this time, the temperature of the universe cooled, and there are many processes, non-equilibrium processes that could have happened here, and we currently don't really understand basically any of them. So the idea is to understand non-equilibrium dynamics within standard model fields, and you'll see exactly the purpose of this talk is this. So as I said, the temperature of the universe dropped from 100 GeV to 150 MeV. If you just focus on the QCD fields, okay, so forget about anything from the electroweak Lagrangian. If you just focus on the QCD fields, for those temperatures, so when you go from this high temperature, this sort of natural temperature in QCD, then at very high temperatures, QCD was a dilute gas of quasi-particles, okay? While when the temperature is around the QCD crossover temperature, remember that the mass of the pion is 140 MeV, when the temperature is around this scale in the early universe, QCD was a strongly non-conformal system and also strongly interacting, okay? So at high temperatures, it was like a dilute gas, and the temperatures get closer to it becomes a strongly interacting plasma. This has happened in our early universe. So the outline of this talk, so first I'm going to remind you about fluid dynamics, and then I'm going to argue that the expanding universe actually provides a nice avenue of research that actually connected to holography in the end, that has not been explored yet, at least to its full potential. And actually, the idea of trying to understand how a QCD can thermalize in the early universe involves solving two problems, actually. At very high temperatures, where QCD is like a dilute gas of quasi-particles, and another one at lower temperatures, where QCD is strongly interacting. Remember that this is an intrinsically non-equilibrium environment, okay? The universe is expanding. There's no way you can do lattice QCD or any other approach. So, yes? I'm going to talk about that. It's much easier. Much easier. Way easier, in fact. That's why I'm doing it now. Okay, so the point is, in order to solve this question, I'm going to divide the problem. Of course, I'm not going to solve the problem here. What I'm going to do is solve two things. I'm going to solve two toy models. One toy model to address the question at very high temperatures, modeling QCD as basically some dilute gas, basically solving the Boltzmann equation. I'm going to show you that it's actually possible to solve the Boltzmann equation in an expanding universe analytically, completely, in its full nonlinear glory. And then, in order to understand what happens QCD in the early universe close to the transition temperature, I'm going to use a non-conformal, strongly interacting plasma. So here is the domain of holography, now applied in an expanding universe. Okay? Okay, so that's the goal of this talk. Let me see if I can get to the end of it. So fluid dynamics is everywhere. That's what this big word means. And of course, it's across vastly different length scales, cosmological scales, planetary scales, and even our own human scale. So this is a car. This is actually a simulation of fluid dynamics. And it's based on conservation laws plus a hypothesis that in your system you have a very large separation of scales, which normally happens. So the idea that you have your separation of scales, you have what we call a macroscopic scale, capital L, a microscopic scale, little l. And there's a well-defined number, actually a bunch of numbers, this is more like a field, called Knudsen number. For those that have studied hydrodynamics or kinetic theory, you recognize this as basically the ratio between what you call small to what you call big. When this is very, very, very small, we call this a fluid. Okay? So, for example, the small scale will be like a meter. Okay? In these simulations that people do with the hydrodynamic equations, the small scale here is a meter. While here, the big scale is 1 meter, and here, the small scale is of the order of the mean free path of the molecules of air that enter in this calculation. So, of course, the interesting thing is the ratio. So fluid dynamics is a low-energy description of strongly interacting systems. It's based on the smallness of this. It's based on the idea that you can do a well-defined perturbative expansion in this small parameter. Okay? The results that I'm going to show at the end will question a little bit this idea, as you'll see at the end of the talk. Okay, but just to be a little bit more clear, imagine that you have a gas or some fluid. What you would call a large scale is like the gradient of a conserved quantity, like the velocity. See the velocity here? That's your big scale. A small scale would be the mean free path here, 1 over n. N is the density, sigma is the cross-section. For example, you can have systems which are actually very interesting because the big scale and the little scale are almost the same. So this is actually what we call microfluids. So these are blood cells. The distinction between the two scales are not that different, but you see people do these things. So what you call small and large in fluid dynamics has been drastically changing over the years. And in fact, if you want to consider big scales L, that are even smaller than this one is related to cells, you start going to particle physics. While here, the microscopic theory that resolves the molecules and their interactions, you can describe using a gas, and the scale is like 10 to the minus 6 meters. You could try to understand what happens if the microscopic scale is now QCD. Right? Why not? So here you have the Cinder model. Here you have the quark fields. In QCD, there's the gluon. QCD is a very simple theory. You have to do everything you can. 98% of all of us here comes just from these 3 interactions. It's a non-abelian gauge theory, as you have seen during the first week of this workshop. One thing that was found, and Nelson Braga mentioned yesterday, is this idea of the quark-gluon plasma. So now coming to the heavy ion part. So what happened and what was found is that once you collide heavy nuclei here, so this is the collision, and afterwards there is a region. So here, there's a collision, the temperature is very large. Afterwards, the nuclei go away. In this region where the temperature is very large, basically by combining these 3 diagrams and 2 properties that come from these diagrams, this one here comes from these diagrams, but this one we don't know how to get from these diagrams, confinement and asymptotic freedom. One thing that emerged that was certainly not obvious in the QCD Lagrange for a long time is this idea of perfect fluidity. Is actually the main connection to holography up to now with QCD, is the idea that this viscosity, the shear viscosity of entropy ratio is a very small number, an order of magnitude at least with respect to water. So this is an emergent property of QCD, and that's the idea of perfect fluidity. Viscosity is very small. The system evolves like a perfect fluid. So this seems to appear even in elementary proton-proton collisions. Okay, before, quark-gluon plasma appeared only when you had nuclei that were very big, but now even in proton-proton collisions, so our boundaries for what we call fluids have drastically changed, and basically in the last year, now even something of the size of 1 Fermi seems to be a fluid, and not only a fluid, a perfect fluid, okay? So of course, there are many unknowns in this field, many unknowns. So first, how does such a fluid dynamic behavior emerge? You see, the right word is emerge. Nobody would look at the QCD Lagrangian and say, oh, of course, there's a fluid somewhere. And it's a perfect fluid, by the way. How does such a fluid dynamic behavior emerge from quantum fields of a Cinder model? Of course, the answer is not known. How can this system nearly thermalize within very, very short time scales? For heavy ions, the time scale is of the order of 1 Fermi over C. That's the time that light takes to go across a proton. How does it do it? We don't know. How can you prove that the QGP is perfect fluidity, or how can you actually show that from first principles? In a sense, start from the QCD Lagrangian, compute, and get the perfect fluidity. Of course, this is not known. But here, my point is that there is a simpler case to study involving non-equilibrium dynamics of standard model fields, like, for example, QCD fields, that is actually simpler than heavy ion collisions, is the expansion of the universe. So here we start with something very small. So this is a very nice picture. This is from Daniel Bauman's lectures, are very nice lectures about this. So basically, imagine the universe expanding. As it expands, clearly, it was never in local equilibrium. So anything that you try to compute here, you have to worry about non-equilibrium dynamics. Okay? So it's a perfect laboratory to start studying these questions. And of course, there are more symmetries I'm going to show here for the expanding universe in comparison to this complicated heavy ion collision event. But there is only one event that we know of to analyze. There's apparently just one universe. And this talk, for all purposes, is multiverse free. We can go back to the multiverse and hydrodynamics later if you want to. So what is the idea here? So imagine that you have your expanding universe. The universe is described by general relativity, at least the state of expansion at the times that I'm interested in. A little bit transition. General relativity works perfectly. And the symmetries are very good for this problem, okay? So you would imagine, for those that don't really study anything about cosmology, you would expect that the metric would be a complicated thing, but it isn't. In fact, the symmetries constrain the metric to look like this. So here you have your time, here you have your space part. This thing is called the spatial curvature. For us, and actually it's a very good approximation of our universe, this spatial curvature is flat, so this k is 0. These will be Einstein's equation that would solve for the universe, and these things can be rewritten in this way. For now, the only degree of freedom that you actually solve is this A of t, this cosmological scale factor. It tells you how the universe is expanding. And depending on how you have your energy density, for example, if your energy density goes like matter, it goes like 1 over 8 cubed. If it's radiation, it's 1 over 8 to the 4th. And if it's a cosmological constant, it's 8 to the 0. You plug this in here, and you find what A looks like. It's a well-known thing. It's all in every textbook in cosmology. So the symmetries that we use are spatial isotropy is homogeneity. So basically, the universe is a sequence. For us, it will be a sequence of flat spaces like this. Okay? This simplifies a lot because the metric just looks like that. It's almost like Minkowski metric. But now there is this expansion. This A of t, okay? This guy is determined from the Einstein's equations. And what it looks like is this. So imagine, for those who haven't seen that, imagine that you have 2 points here at a certain time that we call t0. The distance between these 2 points I would call 1 in some units. As time goes by, that A factor expands, and this distance, while you still call it 1, it's bigger, okay? That's what this thing that I call here, this delta x physical, that incorporates the expansion of the universe here. This is A of t, okay? So when you talk about thermalization in an expanding universe, the good things about it is that, of course, we do applications in cosmology, and cosmology is a very thriving field nowadays. Second, the symmetries are very constraining. Spatial isotropy and homogeneity, they're very, very strong symmetries to solve your problem. You see, even the holographic case that I'm going to show later, that these symmetries already determine the metric, the bulk metric, to a very nice form. And in comparison to, for example, heavy ion collisions, the expansion of the universe is simple. It expands in a homogeneous matter, just that is this A of t thing that takes everything away with it. The cons. In general, your gut feeling is that if you include GR, things get complicated. So you avoid GR at all costs, unless you have to do it, when you're trying to solve any problem, including non-equilibrium dynamics here. So why would the inclusion of something hard or complicated like GR actually help anybody here? So the reason is this. If your goal is just to understand how these standard model fields, or in this specific case, how these fields in the QCD Lagrangian thermalize, how they go from a state completely out of equilibrium to a state of equilibrium, the easiest thing that you can consider is this. Nothing would be easier than studying how a locally static system. So imagine the fields are locally static, but the universe itself is expanding, which is what happens. Okay? So this gas, or this system, inherently is out of equilibrium. So this is just the thing I said before. So the distance increases with the expansion of the A, but locally, this is a technical thing, locally, if you were to compute the expansion or the flow velocity, this guy is like this, 1, 0, 0, 0, 0. Okay? So matter is locally static. However, because of the expansion of the universe, this thing here that we call the expansion rate, you will see in the next slide, it's always given by this. So this is the Hubble constant. It tells you how the universe expands. Because of the expansion of the universe, the system, while it's locally static, it is actually expanding and out of equilibrium. This is by far the easiest thing you can consider in this problem. So the first toy model, as I said, try to understand the phase of QCD, which is very dilute. Okay, so it's really like a little gas of interacting quasi-particles, like quasi-quarks and quasi-gluons. So the most simple model that I can think of is basically the Boltzmann equation, but the general relativistic Boltzmann equation. So in a sense, we have to make compatible the assumptions behind Boltzmann. I put Boltzmann's name here because I'm assuming that this guy everybody knows. So I guess everybody should know Boltzmann too, but his beard was bigger, so probably has to be mentioned. So the idea of Boltzmann was this idea behind molecular chaos. So basically, after a particle hits another particle, it has no idea what is going on. It loses completely its memory. Okay, so until it collides again, then it has no idea what's going on again. So it gets drunk after collision and goes completely crazy afterwards. Okay? So that's the idea that defines a mean-free path, something like that. Okay? And of course, you have to combine that with general relativity. So these particles, they're not in a flat space, but in a curved space-time, in this case, the expanding universe. So one thing that I'm going to show you here that is kind of surprising is that if you get these ultra-relativistic particles, what would be like this little toy model for QCD, in an expanding universe, so basically imagine you have a box, you have your little particles colliding, and time goes by, the box increases, that's the expansion of the universe. What I'm going to show you is that every single non-equilibrium state of this system can be described using a simple, almost 150 years old, non-relativistic gas of Maxwellian molecules that Maxwell himself studied a long time ago. So basically, there is some sort of duality or equivalence between relativistic non-equilibrium dynamics and non-relativistic non-equilibrium dynamics that you see in a few slides. So how do you actually do it? Right? So I'm trying to solve the problem. My first bastard-like approximation is to say the QCD is like a gas. Just do a Boltzmann equation. Of course, I'm going to do the simplest Boltzmann equation that I can find that can actually include the effects of an expansion. So I have, so this is the idea of the Boltzmann equation. The whole point is that you have a distribution function. You see how the distribution functions varies in space and time due to the collisions. Okay, so you have collisions that change the distribution function. This guy, this F, tells you how many particles you have in the volume. So the toy model for this part of the problem, the high temperature part, the weakly interacting part, I have a Boltzmann equation with massless particles. The temperature is very large, so the mass is irrelevant. I have classical statistics. That's a good approximation given our ignorance about the problem. And this is another approximation. I'm going to say that I just have constant cross-section. So this is far from being QCD. But basically, what I'm saying is that particles come in, particles come out of the interaction region, and this thing is described by a constant cross-section that we're going to call sigma. Again, the idea is not to solve something really realistic, but just to start addressing the problem and solving the simplest problem that I can find. But this toy model captures the physics that I need for this talk. And you'll see that even though in this system there is dissipation, I can compute the entropy analytically almost. Okay? So the entropy increases. You can show that the entropy increases, but the fluid itself flows like a perfect fluid. So what is this Boltzmann equation? I'm not going to go into details, but basically the idea is this. You have your distribution function. It tells you how it varies with time. Because of isotropy, nothing depends on space. Okay? And you have to solve this nonlinear integral differential equation. Okay? It seems complicated, and in fact, it is. Okay? So many people start just the mathematical properties of these equations. So this equation here already includes, so this is written for an expanding space-time. And the idea is that we want to find solutions for the distribution function. If we know this, we can compute any property of the system. Okay? If we know the distribution function of particles, we can compute any other property of the system. So how do you do it? So the way we do it is actually very simple. As any of you know, if you have a distribution function, let me call it f for obvious reasons. This is a distribution function, right? In terms of some random variable, let me call x. If you're able to compute all the different moments of the distribution, if you can compute the cumulants in technical terms of this distribution, you should be able to reconstruct the distribution in the end. Okay? Something that you learn in any statistical mechanics or even quantum mechanics class. For a given distribution, if you can find all of its moments, you can recover the distribution. And that's what we're going to do it here. So instead of solving the Boltzmann equation in this form, we take moments of the Boltzmann equation, find an infinite number of moments, and solve them. Okay? This is how it's done. So for example, the first moment that you can think of is this number density, as you can see here. You get your distribution function. You put a factor of energy. This is just energy in the local rest frame. You integrate over all the momenta. This guy gives you the number density of particles. You could do the same thing for the energy density. And in general, you'll define an object that we call scalar moments, which are these guys. So you have energy powers of the distribution function. If you know all of these, you can go back and find this guy. Okay? The goal in the end is to find the distribution function. Okay, so now this is how the miracle happens. We have to do this sort of integrals back in the Boltzmann equation. And this is not clear. It will not be clear for you how to do this from this talk. It's one of those, normally we see in books saying that, one can easily show blah, 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 blah. This is not it. This will be, as one cannot easily show, we get this, okay? So in fact, look at this equation here. This is an exact equation for the moments. Every single moment that you see here is one of those moments of the Boltzmann equation. This m guy here is just the ratio with respect to equilibrium. It's just to be dimensionless. So look at what you have here. You have a first order equation. You have the effect from GR. This is the expansion of the universe right here. All of it is encoded here. And then you have this nonlinear term that basically gives you all that strong nonlinearity in the Boltzmann equation before. It's in here. All of it is included here. This equation actually is simple. I bet any one of you could try to put this on Mathematica and solve, because you see, it's just a recursive relation. If you know the previous moments, you can find the next ones. It's cut, there's an upper bound here in M. Huh? Because of the cross section. If you have a constant cross section, this thing gets all into M. If we were to do, for example, a lambda phi to the fourth, where the cross section basically goes like this, over S, where S is the Mandelstam S, then this thing goes all the way to infinity. So the judicious choice for the cross section was very clever. But we actually only realized that later. These equations, if you can solve these equations, and I'm telling you, you can just solve it in Mathematica, you can get all the dynamics of the system. Everything is included here. So actually, if you redefine a little bit of the variables, just take into account the mean free path and an expanding universe, you get to this little tau variable. This equation here is interesting for the following form. Remember that the plot that I showed you and claimed that the non-equilibrium dynamics of this expanding gas in general relativity could be mapped into a simple non-relativistic gas. That's what this equation shows. This equation, exactly the same equation, was found 40 years ago by Bobilev, Kruk, and Vu, nearly 40 years ago, for a non-relativistic gas in a little box. Imagine you have a box, some particles, non-relativistic, interacting in a thing that we call Maxwellian molecules. So this little non-relativistic system has, in fact, every single state of that system can be mapped into this state that has complete different symmetries, is embedded within general relativity, and etc. So we can actually have a mapping between every single non-equilibrium state in the system. And this you can solve. Of course, again, as one cannot easily see, you can solve this analytically. Okay? It's one of those moments that you look like, okay, where did it come from? It comes from where things come from. I don't know, air. I have no idea. So, but we can show that this thing is an exact solution of this hierarchy of equations for any m. Okay? So if I know exactly how every single moment of the distribution function works, I can go back and compute the distribution function exactly. And in fact, that's what was found in this paper here that I mentioned before. So this, actually, lo and behold, is the first analytical solution of the Boltzmann equation in an expanding system since, I guess, Boltzmann wrote it. Because actually, non-relativistically, it's very hard to describe expanding systems, but because of this trick with general relativity, that it can put the system in locally static, but the universe itself expanding, you have basically a full analytical solution of the nonlinear Boltzmann equation, and that is here. This looks like equilibrium, has an exponential of the energy. There is some sort of redshift factor because of this kappa. This is a complicated function. You can see that is a typical analytical solution because the initial condition involves magical numbers like 256 divided by 243. If you were to put 256.2, it would not be an analytical solution. So it's a typical, things that have basically measure 0. You're never going to find one of those again. But we did find one. So why is this interesting? Because now, since I have the exact solution of the Boltzmann equation, I can go back and compute its entropy. And the production of entropy, in many cases, or actually, the idea of error of time, or the H theorem in the Boltzmann equation, is something that is very interesting. It goes actually to different fields, not just kinetic theory, but also any other field that involves entropy and even decoherence. So the idea that you can show is the following. So if you put this F analytically here, you can see that entropy production. So entropy is always being produced. You see here the divergence of the entropy is always larger or equal to 0. So it's only equal to 0 if you have equilibrium. For this state that we have this analytical solution, the entropy is being produced, and it's only carried by known hydrodynamic modes. Known hydrodynamic modes, I'm not sure if everybody is familiar with. The idea is simple. You have hydrodynamic modes like sound waves. Sound waves have dispersion relations like that. Dissipation would enter here, and here you just have this sound wave. This is the speed of sound, okay? This is a hydrodynamic mode because when k goes to 0, this guy here, omega, goes to 0. It becomes infinitely light as the momentum goes to 0. A known hydro mode is such that the limit when k goes to 0, when you go to a system that is completely uniform, this guy here is a number that is different than 0, okay? It is relevant for several applications within hydrodynamics and the approach to hydrodynamics in EDSFT. And what we found here is that every single bit of entropy that is being produced is carried exactly by these known hydrodynamic modes. And we can actually find, I didn't put the expression here, but you can find the entropy production analytically, okay? And even though the symmetries require that energy momentum tensor has to be exactly the perfect fluid form, so in this system, even though it's out of equilibrium, the energy momentum tensor is epsilon and then 3p or P, 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 and 0, 0, 0, 0, 0 everywhere. So the energy momentum tensor is diagonal, and this guy here is epsilon is equal to 3p if you have massless gas. Even though the energy momentum tensor is exactly like the one in equilibrium, the system is completely out of equilibrium. And in fact, you can prove that this system never equilibrates. So you have an example of a universe that never goes into equilibrium. The expansion is just too fast. Okay? So this, what this tells us for the first part of the problem, to try to understand QCD at high T, is that it could be that even though the system is completely out of equilibrium in the early universe, the energy momentum tensor will look exactly like the perfect fluid form. And one still has to figure it out what happens to this entropy that is being produced. It's not clear the effect yet. Okay, but this is all very nice. But close to the phase transition, QCD is strongly coupled, as I say here. This description using Boltzmann equation is not valid. And how do you study these non-equilibrium processes in strongly coupled gauge theories? Lattice QCD is useless completely for this problem. The only thing you have to do is to jump into the black hole. There's nothing else. Be happy. They're going to the black hole, forget about firewalls, and try to solve the problem. Okay? That's what we're going to do here. So, okay, this is just a cartoon. You already had, full lectures about this. So just the idea of the holography, the gauge string duality. Yes. Yeah, so the lesson for the first time model is this, that at very high temperature, QCD in the early universe, the energy momentum tensor degrees of freedom will look exactly like a perfect fluid, but the system itself will be completely out of equilibrium in general. Completely out of equilibrium. So you're going to have entropy being produced. You have non-equilibrium entropy by a lot of degrees of freedoms that don't actually contribute to the energy momentum tensor because of the symmetries. Once you put this FRW symmetry, isotropy, and homogeneity, you have a lot of degrees of freedom that contribute to the entropy, but the energy momentum tensor is always in equilibrium. And this is a little bit unusual.
But that's a fault order, right? There's no back reaction of the matter on the vector that
Yes, because it's massless. Actually, if the particles are massless, this is an exact solution of the Einstein-Boltzmann equations together. Because if this is massless, A goes like T to the 1/2. This is time. This is an exact solution of the Friedmann's equations, and you can go back and put in the Boltzmann and solve it too. So it's actually a full solution of both Einstein and Boltzmann together. So as long as you have massless fields, this phenomenon that I said, this sort of perfect fluidity of a dissipative fluid, at least according to kinetic theory, will show up. You will see that within the holography regime, this is very different. This is not going to happen at strong coupling. Yes, temperature. The temperature is very large, right? Temperature is very large. I'm not sure. No, yeah, in heavy ion collisions is not possible. No, I think in heavy ion collisions, this phenomenon, this perfect fluidity of a dissipative system, is not there because the symmetries are not good enough. The problem with these symmetries here, maybe this is useful for the rest, is that when you try to produce entropy, right, so you have to produce entropy. Normally, if you look at Landau-Lifshitz, you would see that this guy would go like shear viscosity, bulk viscosity, heat conductivity, and all these transport coefficients. For this specific system, F or W, because of the symmetries, all of these guys are 0. Okay? Shear doesn't contribute. The mass is 0, bulk is 0, heat conductivity is 0, everything is 0 here. So the only fact that this guy here is non-zero comes from degrees of freedom that are not in the hydrodynamic limit. Okay? But this is really because of symmetries. In heavy ion collisions, not the case. You're going to have both terms. And it's not clear at the moment which one gives more entropy. I'm not sure about that. I don't know the answer. Okay? QCD is far from this model. So the only point that I have here for QCD is that I know that QCD is a weakly interacting gas at those ridiculously large temperatures. And I'm modeling, basically, in order to do something with it, I'm considering a gas of massless particles interacting with a constant cross-section. That's the best I can do. Of course, you can actually write down the Boltzmann equation for QCD, and it actually looks much more complicated than that, and is far from being solved. But of course, in hindsight, you choose some very simple configuration, and you find an analytical solution, get happy about it. And now I have to worry about doing the more realistic problem for QCD. But this feature that I said, this perfect fluidity thing, will work, even for QCD itself. Okay, so what happens near the phase transition? Now the system is strongly coupled. The tool to use is holography. You all know about it. So this is just a cartoon of N equals 4 Spring Mills. I'm pretty sure you all had a lot of lectures about it, so I'm not going to go through it. The only interesting thing for me here is that even, of course, at strong coupling, this theory is still a CFT, and I don't want that. I don't want a CFT for this problem because my interest is to understand QCD in the regime where the temperature is of order 200 MeV, okay? And what we know from lattice QCD, this thing here that they call interaction measure, this is 200, this is MeV, this thing here looks like that, okay? So close to the QCD crossover transition, even in the early universe, the QCD Lagrangian, or the QCD fields, were highly non-conformal. So I have to be better than just a CFT. And that's why I'm going to go with N equals 2 star, okay? Good. So just a few remarkable facts about duality. In holography, if the coupling is very large, the string theory gets easier. If you have a lot of degrees of freedom, the string coupling goes to 0, so everything goes nicely and well. If your system is spatially isotropic, this nice little theorem, and you have, if you're sufficiently large and lambda, you have this, yes? This is from lattice. No, that's why I'm using holography. Yeah. So my point is that I want to understand QCD when the temperature of the universe was in this region. Of course, I don't know how to actually solve QCD. I'm going to solve this N equals 2 star model, which is strongly coupled, but non-conformal. So at least this is not 0. Okay? The epsilon minus 3p doesn't look exactly like that, but it's a very good approximation, at least as a first step. Okay? So that's why I divided the talk and the problem into 2 problems. So first, weakly coupled Boltzmann dilute gas, and now strongly coupled holography part close to the phase transition. Okay, so if your black hole that you have in your geometry is if it's isotropic, then eta rest has this very nice 1/4 pi limit. It was very good for heavy ion collisions. And actually, since heavy ion collisions tell you that QCD around the phase transition was a perfect fluid, in the sense that the viscosity was very small, all the dissipative effects were basically 0, or as small as it could be, we can actually conclude that even in the early universe, there was a lot. Basically, the whole universe was made of perfect fluid. Really, truly perfect fluid. Eta rest being very small, at least when the temperature was very small in the sense of the order of 200 MeV. So there must have been a lot of perfect fluid in the universe. The phenomenological consequences are entirely unknown. I don't know of anything that this could affect. I will be very interested if you can think about something. And given that around these temperatures, QCD is not conformal and strongly interacting, the only thing you can actually do in non-equilibrium situations is to consider holography, and the specific theory that I'm going to consider is this N equals 2 star theory in an expanding spacetime. This is an interesting novelty that may not be really familiar to all of you, is that in specific cases, you can consider the case where the boundary quantum field theory is actually in a curved space. F or W is a curved space time, but you can actually do the duality and compute all the observables just as nicely. At least in this example, and the other one, which is N equals 4, one can do it too. So the details, many details are in this paper with Alex Bushel, Michelle Haller, and myself here, in this paper here. So what is N equals 2 star gauge theory? This is the second toy model. Now is the strongly interacting part. It is basically the idea that you have your Spring Mills, you include a relevant deformation of it. So here you have n equals 4 Spring Mills that you've seen in your lectures, but now imagine that there is a correction, a relevant operator is included. So here you have the bosonic part. So you see the bosonic mass, even the dimension is correct, MB2. And here fermionic mass, this is the bosonic operator that is written here. This is the fermionic operator that is written here. This is a well-defined model that has been studied by many people for more than 10 years, actually more than 15 years. And at least for our purposes, the gravity action. So see, this is now in 5 dimensions. What I'm doing is that I have the bulk in 5 dimensions. The Lagrangian in the bulk is exactly the ones that everybody knew from n equals 2 star. We have the metric. You have an alpha field for one of the relevant deformations, another scalar field there, okay? Each one has a different dimension, 2 and 3. And then here you have a potential. This potential comes straight from the string construction. There is a very nice form for it. There's exponentials and hyperbolic cosines. So this model is non-conformal. If you compute the energy density and the pressure, you get this. Epsilon is not 3p. So at least it fulfills the minimum requirement that I want to try to understand what happened to QCD when the temperatures were in this regime. Okay? At least it's not conformal. So this actually comes from there's a well-defined string theory construction. Yeah, it's okay, I'm not going to go into detail, but I can tell you later. Yeah, it's completely well-defined. So, of course, you can do many other models that involve scalar fields where this potential is guessed or sort of engineered to look like something. But at least in this first work, we actually wanted to go with a well-defined model. Also because Alex really pushed for it. And actually, it turned out that using this model was very interesting for the reason I'm going to show you later. So, the bulk has a strongly interacting theory in 5 dimensions, including gravity and 2 scalar fields. At the boundary, you have an expanding universe. Okay? So how do you actually do the duality in this case? The interesting part, and the interesting thing that you use is actually this very nice work by Paul Chesler and Larry Affey from 2013, what they call the characteristic formulation of gravitational dynamics in asymptotically ADS5 spacetimes. But if you really go down to it, is basically a very nice way to foliate space-time to actually make some of the symmetries manifest. And this sort of form that I'm going to show you and discuss a little bit now is actually very good for numerical calculations. That's why Chesler and other people did a lot of numerical calculations in non-equilibrium ADS using this formulation. The way it works is the following. So here you have your metric in 5 dimensions, the bulk. Okay? So normally you would use coordinates that you would call Pfefferman and Graham, okay, or some other system of coordinates. This one is much more like Eddington-Finkelstein coordinates, okay? So for example, if you were to do your retarded Green's function analysis, in normal coordinates, you have to say that you have incoming waves at the horizon, and there is as you said, and Nelson was talking about yesterday, we have 2 solutions, something that looks like that, and another one that looks like that. So an incoming and outgoing, or maybe the opposite, I don't care. But basically I have 2 solutions close to the horizon, you have to pick one, etc. In this formulation is very nice. It's already automatically there. The only thing you need to say is that you need a regularity at the horizon. If the geometry at the horizon is regular, you solved, okay? Several problems become much more simple in this language, and I strongly suggest for anybody doing non-equilibrium dynamics to try to use this sort of procedure. So you see the metric is not diagonal anymore. So you have this spatial part, this sigma field, you have this A field here, and here, as it happens in Eddington-Finkelstein, this guy here is not diagonal anymore, okay? So how do you actually impose that you have like an FRW system, why the QFT is still expanding in the universe? So the important part here is that because of isotropy and homogeneity, the metric becomes just this. You really just have to solve for 2 functions that are a function of the holographic coordinate r. Okay? So it becomes a simple solution, and the way you expand the near boundary terms before, for example, this field here, this sigma, that it has to do with the spatial part here, it would be just like 1 over r. But if you want to put this in FRW, you just put A over r. Okay, and where this A of t is the solution of Friedman's equations. And you can do that for every single boundary condition. So every problem that you had before is completely well defined here. And in fact, this sort of coordinates, the characteristic formulation, or Eddington-Finkelstein, simplified the problem a lot. This idea of putting strongly coupled dynamics in FRW was tried and was studied in 2010 by these Greek guys here, the Tradris and these other guys. And what they did was said, okay, let's see what happens to Supering Mills in FRW, how Supering Mills behaves in an expanding space-time. The paper is a very interesting paper. It's complicated because they don't use the system of coordinates that we use. If you use Eddington-Finkelstein, the solution comes out analytically, clearly, in a few lines. This defines n equals 4 Supering Mills in FRW. N equals 4 Supering Mills appears as a limit of the theory that I have if you throw away the deformations. Throw away the masses of the bosons and the fermions, you get to n equals 4. The solution is this. And actually, for those that remember this, even though n equals 4 is a conformal theory in flat space, in curved space-time, actually there is a conformal anomaly, and you can see that the energy density, for example, looks like the usual energy density with the t to the 4th, plus a correction here that has to do because of the fact that the geometry is curved. Okay, so there's a conformal anomaly in the pressure, energy density, and etc. So this was done in 2009, 2010, and what we did was to generalize this for n equals 2 star. There are many aspects that you can do in this problem. The aspect that I'm going to focus now has to do with hydrodynamics and the ability or the validity of hydrodynamics as a well-defined expansion. Okay? So, yes? Oh, yeah, so you can compute every single quantity that you had before. You can compute. In your QCD? Oh, certainly not, yes. But I have no idea how to do anything otherwise. Because
Considering now a toy model where you have only non-interacting hadron or weakly interacting hadron, that put them in FRW.
Because then I would miss the most characteristic property of QCD in this regime, which is perfect fluidity. I want a description that is strongly interacting, non-conformal, and it's a perfect fluid. I want 8 over s to be 1 over pi. If I put a bunch of hadrons, 8 over s will be 10, because they are weakly interacting. So I missed the key defining property that took 15 years for us to learn at RIC. So it's a choice. But I agree, you can certainly do that just fine. Go through all this exercise with all the different models. My point, actually, is to push towards this sort of application. There's a lot of stuff, non-equilibrium dynamics, that is not being explored at all, that could be done within even a cosmology context, or just to understand thermalization by itself. Okay? And I think it has not been explored yet. This is the only paper that I remember before us. So let's talk about the hydrodynamic series, right? Everything that people understand. This thing here is made of molecules. The mean free path is very small, 10 to the minus 6, but clearly this is a fluid, right? We have a fluid here. The air is a fluid, water, we drink and be happy, beer and everything else. So the idea about hydrodynamics is that they have this Knudsen series expansion. As I said before, you have a macroscopic scale and the little microscopic scale. And the whole point of this is the following. For example, imagine that you have your T mu nu, okay? Your energy momentum tensor. In fact, interpret this as the expectation value of T mu nu, okay? So the first thing that you can do, you say, imagine that all the viscous effects are 0, or that the little L over big L goes to 0. This is the equilibrium or a perfect fluid, a true perfect fluid, okay? So here's just the ideal gas. Then you would think, oh, okay, so now if this is an expansion in viscous corrections, I can go like this. I put my small number, and then I get new term, okay? This is known as Navier-Stokes equations. non-relativistically, and even relativistic, we call it Navier-Stokes. And then you could go further. This term here became very popular and interesting after people defined it, like Minwala and Rangamani. They did the fluid gravity, let me see, fluid gravity correspondence, okay? So basically, it was a very nice way to organize or maybe create a way to define this hydrodynamic expansion directly from the holographic setting, okay? You can go to higher orders. This is second order hydro, third order. You could do whatever you want. Of course, this is based on two things. One, that this expansion is at least well-defined, okay? And at least stable. So in a sense that I start with these equations I can solve in a computer, and I put these equations I can solve in a computer, and I put these equations I can solve in a computer, okay? Yeah, like for a gas, it would be a mean, small, yeah. You'll see that, yes. Good point. In general, it depends on the process, right? So you actually have a very different Knudsen numbers. For shear viscosity, you have the mean free path. I'm talking about quasi-particles here. So you have the mean free path associated with momentum diffusion. For bulk viscosity, you would have the mean free path associated with particle changing processes. So the Knudsen number is not just one number, it's a bunch of different ones. At weak coupling, I can certainly understand where it comes from. At strong coupling, the general guess is just the interparticle distance. Then L is of order 1 over T. Because at strong coupling, you don't have quasi-particles. Yeah, so at least if it's, I think this is the smallest thing you can think that it still makes sense, the interparticle distance. Maybe some pi somewhere, but. Okay, 10 minutes, yeah, I'll finish. So the whole idea is this Knudsen number expansion. This is well defined in kinetic theory. Okay, some people may not know. This idea of expanding Knudsen number was not invented in the fluid gravity. This was invented in 1923 by Chapman, but within the Boltzmann equation. Of course, the nice thing that they did it was that at strong coupling, nobody had a clue how to do this expansion. At strong coupling, these guys did that. So this idea of expanding in powers of Knudsen number it's old. Within the gauge gravity duality, it was done by a bunch of people here around 2006. And in our case, what does it mean? It means the following. You have the energy momentum tensor. It's expanding around equilibrium plus corrections, viscous corrections, that depends on the gradients. The gradients in this case are like the gradients of the flow or the A dot. So this is like the Hubble expansion, okay? So basically the idea, this Knudsen number expansion have to organize this expansion in well-defined powers, okay? So for the energy density, we have something like this. For the pressure, C, for example, would appear a bulk viscosity. This theory is not conformal, so there is a bulk viscosity right here, okay? And it's known what its value. And one thing that we could compute, I'm not going to go into details, and that's the first thing we computed. Can do many things, but the first thing is the entropy production. We want to understand how much entropy is produced because of the expansion of the universe in this strongly interacting non-conformal plasma, okay? And it amounts to find the parent horizon. It is defined in this geometry like this. You take the derivative and you compute it, okay? This guy, this is the thing out of equilibrium, okay? This is the amount of entropy that's being produced. If it's in equilibrium, this is 0, okay? The cool thing about this model that justified n equals 2 star is that we can actually do this analytically. So, of course, there's a bunch of complicated terms that I don't want to show you here or to bother you with this. The important thing is this. There is a quantity that we call omega that gives you directly the entropy production. And, okay, it's a complicated thing, but my point is that it's a well-defined sum of quantities that you can compute in the theory. Okay? Delta, it's related to the dimension of it. It's a constant that depends on the dimension of the field. So actually, this result, we have two contributions, one from the dimension 2 and one from the dimension 3 operators that you put in. Because for n equals 4, this is actually 0. N equals 4 does not produce any entropy. It has to be non-conformal to produce entropy. I may have the details afterwards there. The point of this is that this Knudsen number expansion is done within this n here. Each power of n is like the Knudsen number expansion. Okay? So you can go to first order. First order will give you the bulk viscosity. Second order will give high order coefficient, etc. So if we use single component cosmologies where A has this form, you find that this complicated thing here, you find an expression for it, analytical. The important thing of it is this. This thing grows like a factorial. So this means that entropy production, which is one of the key observables for the hydrodynamic expansion, the definition of the production of entropy in the fluid is actually not a really well-defined series. Okay? So this is the divergent series. This is the second example that I know where the hydrodynamic expansion actually diverges. So it's not well-defined at all. Okay? Of course, we all do quantum field theory, and we know that most of the things that we compute are actually, if you were to compute it to higher orders, it will be divergent too. QED is a very nice example. The issue is, if you actually go to every order in this expansion, if you start doing this problem actually has some instabilities. So if you try to define the problem using the expansion, you find that it's not a well-defined expansion, it's a divergent series. And every single term actually gives you, besides the equilibrium, gives you some type of instabilities, okay? So this actually is the first analytical proof of the divergence of a hydrodynamic series. So the Knudsen series that we use to basically define hydrodynamics has 0 radius of convergence. And this points to the idea that there must be, maybe, a new way to do hydrodynamics that does not necessarily rely on this Knudsen number expansion that, at least in some cases, at least in the 2 cases that we can actually do the calculation, is not really well defined. Such a theory may involve the mathematics of resurgence that I have negative time to talk about, but it's just, I'm going to say that it's something that has been done by a bunch of people, so mostly I would suggest you take a look at works by Dunn and Onzal, and also Sherman and Heller and Yannick. So basically the idea, as you remember, if you have a divergent series, what happens, you start putting corrections in the series, and it goes okay. And at some point, when n is very large, the order of the series is very large, then boom, this thing starts to diverge, okay? So the idea with resurgence is to write your expansion series in a different way. It's not just a normal simple power law. You would have your normal power law plus some sort of non-perturbative quantities which sort of plays the role of instantons if you were to do an expansion. But actually, this can be done for hydrodynamics. This was done by Heller and Spalinski in 2015. So we actually did this. We got that term, the one that gives you the powers that diverge, the hydrodynamic series diverge. And what we did, we actually did a Borel sum, okay? And we looked at the Borel singularities. In all these works, including resurgence, they have to look at the Borel singularities and see the structure. And lo and behold, what we actually found is that the Borel singularities of this very complicated expression are nothing but the quasi-normal modes of the black hole. So it's not clear if this is a coincidence. I don't think it is. Quasi-normal modes don't show up for no reason. It could very well be that this complicated mathematics of resurgence that are present in the hydrodynamic series actually can tell information about the black hole quasi-normal modes. We computed this and checked up to order 10 in the quasi-normal modes of the system. So the conclusions, the early universe may be the simplest way to study how standard model quantum fields thermalize. Certainly easier than heavy ions. The perfect fluidity of the early universe, a few microseconds after Big Bang, is an emerging property of the standard model out of equilibrium. It's not clear at all from first principles, not yet. One can do and solve exactly some nonlinear kinetic models in an expanding universe. This showed you the first analytical solution of the Boltzmann equation. It'll be interesting to see if you can use that for cosmological perturbations or some other applications. Due to the strong coupling in the QCD phase transition in the early universe, this new equilibrium dynamics can only be studied using gauge gravity duality. There's no other tool, no other tool. And I think I just want to emphasize that this opens up really a nice avenue, a new thing of research, new area of research, where holography can be very insightful. Basically, I mean, for all the reasons, it's the only game in town, so it has to be insightful by definition. So this toy model of QCD that I had at strong coupling, which is the n equals to star theory, behaves as a perfect fluid, but the hydrodynamic expansion has a 0 radius of convergence. There may be some different way to do hydrodynamics. It's not clear yet what it is, but I'm certain that new ideas are needed to go forward, and I would encourage some of you, and mostly the students, to start thinking about these things and try to connect hydrodynamics, quantum field theory, expansion of the universe, and everything else.